Hi everyone, this is Dr. Hopkins recording another video for Physical Chemistry, Chemistry 472. And today what we're going to do is talk about gases, or at least introduce gases. Alright, as most of you know, gases are one of the three, ostensibly there are other kinds of states of matter, but three fundamental states of matter, or principal states of matter: solid, liquid, and gas. Okay, so gas is one of them. Gases are not more important than solids and liquids, although as you'll see as we go through this course, we'll talk a lot more about gases, but we're going to kind of explain why we use gases. And most of it is because they're the simplest to describe, right? So a gas phase is the one where the intermolecular interactions are pretty much as small as they can be. Okay, so if we have a solid and a liquid, we have intermolecular interactions that are going to depend on structure. Of course, we're very interested in that as chemists, but for the purpose of describing thermodynamics, gases are much easier. And so basically, we can describe the properties of the gas, or the state of that particular gas, using a few fundamental physical properties. And we have the mathematical description, or the mathematical equation, that just about every incoming first-year student can recite, Pivnert, or the ideal gas equation, which is an equation of state, so describing the state of the system based on an equation with variables. Okay, so where we have pressure, volume, temperature, and the number of moles. We also have a proportionality constant, which is the ideal gas constant, or ideal gas constant, R. Okay, so let's describe what pressure is. So pressure is force per unit area, all right? Okay, so we have force, the unit of force, the SI unit of force is a Newton, area would be meters squared, so the SI unit is Pascal. Okay, Pascal is a Newton per meter squared. There are other units that we probably will use more often, although Pascal's work, such as torr, millimeter mercury, atmosphere, and bar. Just to give you some context, 1 atmosphere of pressure is 101,325 pascals. It's much easier with a bar, which is 100,000 pascals. So anyway, so what does pressure mean molecularly? It's just the pressure of this is the gas particles colliding on the barriers, the walls of the container. So pressure is something you feel at a barrier. And in all cases, if we're at equilibrium, the pressure will occur. So we will not have pressure variance. If there is an ability for pressure to be exchanged across some barrier, it will, until the pressure is exactly the same on both. So I show high pressure versus low pressure. If this is a piston, the high pressure will push the piston into the low pressure area so that the pressures equilibrate. In a main example of that is if you have like a beaker of water or a beaker of something open to the atmosphere, the size of the liquid will adopt the size it needs in order to push back on atmospheric pressure, right? So for example, if you drop the pressure, atmospheric pressure, the volume will expand, expand, expand. If you drop the pressure of a liquid enough, eventually it will boil and become a gas. So, and then we have temperature. Of course, this is something we're all familiar with as a measure of thermal energy. Units are always Kelvin. Any other set of units, even Celsius, are not very useful because they have a zero in the wrong place. So you can't have negative temperatures, this idea of negative temperature. And so then we introduce the zeroth law of thermodynamics, which is something we all kind of fundamentally know intuitively from interacting with the world. But if you have two systems that are in thermal equilibrium with a third system, they're all in equilibrium. And basically what that means is as long as there's a boundary with heat flow, if you have something that has, say, I show this example of a pot of water boiling. It's not a very good picture. So you have the oven, the pot, and the water. If they're at equilibrium, they're all at the same temperature. So even though the heat capacity of the pot may be a lot lower than the heat capacity of water, it will always come to the same temperature, right? So there are no thermal gradients at equilibrium. Anyway, so that's temperature. And then the last one is volume. Volume is just a measurement of the size, the area with another dimension, if you will. And in terms of a gas, the volume is set by the size of the container, right? So we just need to know what the size of the container is. If we have a liquid or solid, obviously the volume is set by the density. So then it's a property of the material itself because of things like intermolecular interactions and structure and so forth. So the units of volume we're going to use typically is liter or decimeter cubed, right? So you have cubic length units. A milliliter is 1 centimeter cubed. And so those are the units we end up with. So we have pressure, volume, and temperature. Those are our variables. The gas constant, R, and then I'm not describing N for number of moles, but of course we all should know what number of moles is at this point in our chemistry career. And the gas constant is going to change, so it's a proportionality constant to make sure both sides of the equation are the same, based on the units of each of the properties. So I give you 3 examples where liter atmosphere, liter bar, joules per mole Kelvin. So those are all examples of the value of R. So in the next video, what we're going to do is we're going to manipulate the ideal gas equation, actually talk about what are the kind of assumptions, right? So what are the assumptions that go into developing the ideal gas equation, and then we're going to move into other gas equations. But for now, what we have are a set of properties that we can use to describe the state. We can set them up in an equation and then manipulate that equation.